she just did one trial, and she flipped her coin 73, 100 times, got 73 heads. So her sample proportion of getting heads, there's a proportion of heads, her sample proportion of getting heads is 73 out of 100 is 0.73. That's her sample proportion, okay? A simulation was run 200 times, and the average, and this was done with a fair coin, so just taking a regular coin, the computer simulated, flipping it 100 times, and one of those times only 35% of them were heads. Another time, 37% of them were heads. And they did this over and over and over again, 200 times. Okay? So this is all doable, because we know for this is done with a fair coin. Her coin put her at 0.73. 0.73 would be way out here, which never happened by chance. See that? So what would you say is true? 73 of the computer's next 100 coin flips will be heads. You're saying if you run a simulation one more time, it'll be 73% of the time heads. Now you have no way of knowing what's going to happen the next time you flip the coin over time. So that's predicting future events with some sort of certainty, which is impossible. Number two is that 50 of her next 100 coin flips will be heads. Again, how do you know what's going to happen the next time you do it? You don't know what's definitely going to happen. And then obviously 3 and 4 are opposites of each other, so it's one of those two, right? Raise your hand if you think her coin is not fair. Straight up. Raise your hand if you think her coin is fair. Why? But there's not enough evidence to prove anything, right? That's why they say which is most accurate. But our coin, so when we ran simulations with a fair coin, 0% of the time did that happen by chance. So this is almost as conclusive as it's ever going to get. But there's a 0% chance that her 73 happened with a fair coin. Which means your conclusion, the best conclusion is that her coin is not fair. Because with it, it gave her a result that never happened in 200 trials, and that didn't even happen once in real life with a fair coin. So the fact that it happened with her coin is absolutely suspicious. And so the better answer is that it's not fair. Nathan. Perfect. Anything's possible. So is it possible that it's a fair coin? It is possible, but it becomes more and more unlikely. The further your data value that you actually got falls outwards, the more unlikely it is. Does that make sense? Okay? Well, so not what's possible, because anything's possible. It's how probable it is. And this is as close to not probable, as close to not possible as we'll ever get. Okay? Alright, so that's for the record, do you know what a fair coin is? A fair coin is one that has an equally likely chance of winning as a tip. An unfair coin would be one that's rigged, like it's weighted a certain way so that it has more chance. If you even stuck a small piece of gum on one side of the coin, you would throw off the weight distribution and you'd make it less fair. Does that make sense? So after doing this, I realized, or we realized, that a fair coin might not be a concept that you're familiar with. So, all right. So we jump to sample means. going back to that proportion of juniors or freshmen, proportion of Hamburg High School students that own a cell phone, that's a yes or no question, right? So you're looking for the proportion that said yes versus the proportion that said no. Sample means you're going to find is different. So if we were doing a sample mean question, we might say, we want to know the average number of texts that Hamburg School students send per day. So to figure that out truly, you have to get that data from every single person. But that's not practical. So what we would do, and like Maggie said yesterday, is sample 50 people. So I would grab 50 people and I would say, Bo, how many texts did you send yesterday? Connor, how many did you send yesterday? And I would grab those 50 people's numbers, and what would I do with them? Average them. Okay? So that average for my 50 people that I chose was, I don't know, 119 texts that day on average. Okay? Is that what the average is for the whole school? No. Is it in the ballpark? Hopefully, probably, unless we got really unlucky or like underestimated because we picked people that don't text a lot, or vice versa. So what would you do? You would throw those 50 people back. You would grab 50 more people. Okay? So you would ask Evan and you would ask Nathan, and maybe Bo fell in that example too. You'd ask them how many texts. You'd take all those numbers for those 50 people and you would average those again together. And you didn't get 119 that time, you got 127. So now what's your best guess as to the whole school? You would average those averages, yes? You take the 119 average of the first 50, the 127 average of the next 50, and you average those averages. And the more you do this, that's going to be the mean of the means. The mean of the means is going to be very close to what the actual population is. Do we follow? So, similar concept, but you're taking numbers and averaging them as opposed to just proportions. Okay? So, say we are investigating the heights of 16-year-old American males. Say we know that the population mean height is 65.3 and a standard deviation of 4.2. Let's say we take a sample of the males and the sample size is 30. Forget that they're 16 years old. That number's in there just to throw you off. So, will the mean height of the sample always be 65.3? No. Because in a sample, we may get unlucky or lucky in picking, I guess this is what, heights? Picking taller versus shorter kids. Could it be very different? Absolutely. I could just get, I'm only grabbing 30 kids. I could just so happen to have picked 30 that were short on average. Okay? So there's another program, there's another simulation we're going to have to run, and we're going to run it with an average, that's the average of the population, 65.3, a sample size of 30, a standard deviation of 4.2, and we're going to run 200 simulations. So, again on my website, I have added this sample mean, which now is the bottom one. So I played with one sample proportion, one sample mean. So on this particular problem, we've got, yes, not just, yeah, I want you to wait through this, please. 65.3 is what we know our population average height is for 16-year-olds. Standard deviation, 4.2. I'm going to run 200 simulations, sample size of 30. Run my simulation, okay. So, we are concerned with this column, our sample means. Our average height, we know for the population is 65.3. On the unlucky end of things, when I took 30 kids, the lowest average height I got was 63.09, which is 2 inches
a little bit more than 2 inches less than the mean. So that's a pretty big difference if you're talking about the difference in the average. So on the low end, 63.09, and on the high end, 67.54. So I'm going to record those numbers. 63.09 for the minimum. Does anyone remember what I said for the max? 67.54. Which, no surprise, that surrounds the actual 65.3 pretty well. Not perfectly, but this is, essentially real-time calculations. Now, I just did that 200 times. If I go back to my simulator and I average, and that's this number here, I average all 200 of those averages from those 200 samples taken. My average of the averages is 65.29. That should be essentially the same thing as the population average, which it is. 65.29 versus 65.3, okay? And when you look at the standard deviation of all those averages, meaning how much they vary from each other, it should be very, very low. Because when you're taking the averages, the variation level should be of your averages should be very low. So 0.75. If I took 500 samples, I think that standard deviation of the means would get even lower. So there's essentially little to no variation. How does the variability of the sample means, so this number, 0.75, compare to the variability of the population? And the population is really saying, grabbing one person from another person, how, what that means, right? 95% of the people will be within 2 standard deviations of that. But the variation of your averages will be much lower. That concept I'm not overly crazy about. State the average of the sample standard deviation. So if I look at my average of the standard deviations, that would mean I would have to add up all of these standard deviations and divide by 200, which I wish they did for me. I'm not going to do that. Let's just say I average the smallest with the lowest. 2.69 with 5.6. 2.69 plus 5.6 divided by 2. 4.145. Let's say it's approximately 4.145. And that should be fairly close to the standard deviation of the entire population, which it is. So it's about the same. Okay. Back to notation, kind of similar to yesterday. Yesterday our sample proportion was this little p with a hat versus our population proportion was the p all by itself. Today the sample's average is x bar. The population's average is this u. Usually that bar is not above it, so don't really worry about that. So here's a different scenario. This Mr. Weiler took a sample of 30 16-year-old males and found the average height of the samples to be of his sample to be 66.4. So was his sample taller or shorter than the population? Cameron? His sample had a height of 66.4. That was just his sample. Is that taller or shorter than the population average? Taller by about 1.1 inches. Okay? So the sample mean, x bar, is 66.4 versus the population mean, was 65.3. So what our simulation is we're going to look at is, does it look like that sample came from the population? Or was it taller because he got his sample from the basketball squad, right? Something like that, okay? So I'm going to look at my simulation chart and look at the distribution of all of the averages of my samples. Now 66.4 is right around here, okay? That's not overly off the chart, is it? It's kind of in the middle 95%, we could say, right? So I would say it's pretty possible that he just got lucky. He just got lucky and happened to grab some taller kids. So do I believe the sample came from this population? Yes. Because, and if you want to explain it in terms of what we just saw on that chart, because 66.4 falls within the middle 95%. I guess, of our distributions. But then it says quantify this then. We know, generally speaking, it's in the middle 95%, but quantify how likely it is that this came from the population. Give me 1 second, Nathan. So if I go back to my numbers, and I'm going to go here, and I'm going to grab, what did I get, 66.4? How many are 66.4 or higher? From here and down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15. In my particular simulation, 15 of them are higher than 66.4. So there is a 15% chance. Whoops. There is a 15% chance that Mr. Weiler got a higher sample mean due to luck. Which means there is an 85% chance that he got a higher mean due to some sort of bias, whether it's taking it from the basketball team or taking his people from, I don't know, the Gronkowski family, I don't know, but due to some bias. Something that we would be able to say, he got the taller people because they were basketball players or because they were Gronkowskis, whatever you want to go with that. Now you might say, like, and this is, again, this is personal sensitivity to these numbers, well, an 85% chance, and I'm going to say, yeah, he didn't pull it from the general population. He pulled his people from the basketball team. Statistically, though, the acceptable level is, the cutoff is like 5%. Okay, 5%. So anything that's not 95% isn't enough to draw a conclusion. So says the world of stats. Okay, so there is a cutoff in the stats world. All right, flip over. Nathan, what was your question actually before? Yep, because that's the 95% cutoff. Yep. Yes, you may. Okay, last kind of new scenario to look at today is this sample of 50 ripe oranges taken from a large orchard. And we're going to use this sample now. We're going to use this sample to try to figure out what the average weight of a ripe orange is. Okay? Because we can't go out and take every single ripe orange in the world, weigh it, and average all of those. Can't do that. So we're going to have to let our sample, be our guide. So when we did this and we took 50 ripe oranges, the sample average weight was 212. Does that mean that's the average weight of the entire population? No. But it hopefully puts us in the ballpark unless we got super lucky or unlucky. Morning. Yes. Yeah. So that was our sample's average weight. Our sample's standard deviation, meaning of our 50 oranges, they didn't all have the same weight, right? They varied from each other. So the standard deviation of that was 34. So this wants us to, and you have to bear with me on this one because this is a little bit tricky. We're going to run a simulation as if the population average was 212. Okay? Even though we only got that number from our sample. We're going to run it as if the entire world's oranges that are ripe have an average weight of 212, and using also that standard deviation number. And it wants us to state the 5th percentile cutoff and the 95th percentile cutoff. So how many simulations does it want me to do? It doesn't say. I'm going to do 100 just because 5% of 100 is an easy number to calculate. So 212, standard deviation 34. Number of simulations, I'm going to do 100. How many sample size? I'm taking a sample of 50 oranges. Run my simulation. Okay. So the 5th percentile cutoff would be the bottom 5. So 1, 2, 3, 4, 5. These are the bottom 5 numbers, which means what's the 5th percentile number? What number on my screen is bigger than 5% of the population? 203.5. This number is bigger than 5%, 5 out of 100. So my 5th percentile sample mean is 203.5. And then we want one that's bigger than 95% of the others. So this is my 100th, 99th, 98th, 97th, 96th, 95th. This is the 95th number. So that means that this next one is greater than 95 of the numbers. So that would be 219.8. Okay? So, what both C and D tell us, which I skipped those, is that by using the 5th and 95th percentile values based on our original sample, we have actually found the lowest possible population mean and the highest possible population mean that could have resulted in that sample mean 90% of the time. Ugh, that's a lot. Let's read that again. We have actually found the lowest possible average and the highest possible average that could have resulted in this sample average 90% of the time. This is a 90% confidence interval. So here's what it tells us. Our one sample gave us 212. So we are going to say with 90% confident, so say we are 90% confident that the actual population's average weight will be between 203.5 and 219.8. Okay, your one sample is just that. It's just one sample. So to say that the whole population would have something of 200, a sample weight, a mean average weight of 212, just from one sample, you can't say that. But we know that it will probably be, we're pretty convinced it will be around 212. And these numbers give us that cutoff. We're 90% sure it'll be somewhere between 203.5 and 219.8. Nathan. Is the range of where the actual population average would fall. Okay? If God, if we actually could take all the oranges in the world and we found out that the actual average was as low as 203.5, well then we got abnormally lucky that our sample was that high. And on the flip side, if we find that the population weight was 219.8, well then our sample was abnormally low. But we're going to assume with 90% confidence that the population's weight would be somewhere between those two numbers. Okie doke? All right. So